In this video, we are going to study two problems where we're taking a look at the rate at which some sort of substance, in one case a vitamin, and in another case caffeine, but we're going to study how fast the substance is removed from the bloodstream, starting from a peak amount and then reducing a certain percentage each hour. And our goal in each case is going to be to come up with a formula where we can just plug in how many hours have gone by, and the formula should tell us how much of the substance is left in the bloodstream. Problem number one is the easiest because we're dealing with a vitamin starting at 300 milligrams, and it's simply reducing by 20% per hour. Problem number two is more complicated. It's caffeine. We're starting at 80 milligrams. What makes it tricky is we're not told how much is being eliminated each hour. Instead, we're told that half the caffeine is eliminated after 5 hours. So we don't know how much per hour, but yet we're supposed to come up with a formula that is per hour somehow from the fact that we know that half of it is gone in 5 hours. We have to get everything else, including a formula. So before we get to the more difficult problem, number two, that's called half-life, by the way. When you the time that it takes for half of a substance to be eliminated is called the half-life. So before we get to the half-life problem, let's take a look at the easier problem first, just briefly. So the idea was this. First of all, if you're subtracting 20%, if you're starting with 100% of something and you're taking away 20%, well, the amount that you have left is going to be 80%. So it's actually quicker just to calculate 80% in the first place rather than subtracting 20%. So that's what we're going to do. Anytime they say the amount is being reduced by 20%, we're just going to multiply the original amount by 80%, and 80% is the same thing as taking away 20%. So one quick example, if I wanted to do 20% of 300, because we're starting with 300 milligrams and we're losing 20% each hour. So it would be helpful to know what 20% of 300 is. Well, the way you calculate that is 20% as a decimal is 0.2. So if you do 0.2 times 300, you're going to get 60. So 60 milligrams is 20% in this case. So that's how much is disappearing. So if I want to find out how much vitamin will be left an hour later, I need to take the original 300 and I need to subtract the 20%. And that turns out to be 240. So I'm saying again that rather than taking 20% and subtracting, it would be easier to start with 80%. Okay, 80% of 300 is the same thing as multiplying by 0.8. So if I take 300 times 0.8, that also turns out to be 240. So it's the same thing. So from now on, I'm going to use this method. Whoops, my circle missed. How did I do that? So looking at it that way, okay, so each time I'm taking the previous amount. So I got this by doing 300 times 0.8. All right, 80% of 300 is 240. Same thing as taking away 20%. Now, if I want to take another 20% to find out how much is left the next hour, then I need to make this 80% again. So if I take 240 now and multiply that by 0.8, then that's going to tell me what I have here. Alright, that turns out to be 192. So I'm just going to do that over and over again. So each time I need to reduce this by 20%. In other words, each time I need to make this 80% of what it was. So I'm going to take the previous number and multiply it by 0.8 over and over again. So 192 times 0.8 is 153.6. 153.6 times 0.8. 122.9. I rounded a little. And 122.9. Find 80% of that. Alright, so here's a good estimate of how much of the vitamin will be left. Notice that these numbers are getting smaller and smaller because each time 20% is disappearing each hour, like it said. Now, we are able to come up with a formula by looking at the numbers that are making up these numbers. In other words, I'm going to do this process again, but this time I'm not going to actually multiply 0.8 times 300. I'm going to leave it the way it is and really do it out the long way so we can see the moving parts behind it. So let's start over. Okay, we're doing it over again the long way, trying to find the formula. So if we start with 300 milligrams, then like we said before, if we want to find out how much is going to be left in an hour, we need 80% of this will be left. You know, minus 20 is 80%. And the way we did that, of course, was we did 300 times 0.8. Okay, you know what, maybe let me color code this. So watch this carefully, because each time I'm doing the previous amount and then I'm multiplying by 0.8. So I'm going to show the previous amount in blue, and then I'm going to show the 0.8 in red. So the previous amount times 0.8, that's that's the new amount that's less. This is 20% off, it's 80%. Now, if I want to know an expression for how much is going to be left after 2 hours, again, I need to take the previous amount and multiply it by 0.8. So the previous amount is this whole thing. So I'm not going to multiply it together. It would give me 240, but this time I'm just going to leave it in this form. So here's the previous amount. It's 300. You know what, maybe I'll put it over here. Okay, because I'll need the space in a minute. So here's the previous amount. Alright, all of that, 300 times 0.8, that's the previous amount. But I need to take the previous amount and multiply by 0.8. Remember, that's what we were doing over and over again here. Previous amount times 0.8, previous amount times 0.8, previous amount times 0.8. So that's what I'm doing still. Previous amount times 0.8. Now this is the previous amount, but I need to take it and multiply it by 0.8. Alright, so the blue is the previous amount, and then the 0.8 is in red. So if I want an expression for how much will be left after 3 hours, again I need to do the previous amount times 0.8. But now the previous amount is 300 times 0.8 times 0.8. It's all of this. So there's my previous amount. And here's my times 0.8. Okay, hopefully you can begin to see the pattern here. I'm going to do it again. The previous amount times 0.8. So here's the previous amount. 300 times 0.8 times 0.8 times 0.8. All of that is the previous amount. But now I need to take that and multiply it times 0.8. Okay, so it's the previous amount times 0.8. And I need to do that one more time. The previous amount times 0.8. Okay, so here's the previous amount. 300, 1, 2, 3, 4. Okay, that's the previous amount. And now times 0.8 reduces it by 20%. Okay, so these expressions, look, if I put these ugly expressions in my calculator, I would get the same numbers I had before. Alright, if I put 300 times 0.8, 0.8, 0.8, 0.8, that's going to give me something very close to 98.3. Alright, I'm just showing what was happening behind the scenes. And the point of that was this. Hopefully you can see now that another way to write this would be 300 times 0.8 squared. And this one would be 300 times 0.8 to the third power. And the next one would be 300 times 0.8 to the fourth power. And the last one would be 300 times 0.8 to the fifth power. Okay? And we could even look at this one as 300 times 0.8 to the first power. So I'm sure you can see the connection here, that each time it's 300 times 0.8, and then the power is the hour. So I can easily make a formula once I recognize that no matter what, and so here's where I'm going to put my formula. If I want to know what's happening, how much vitamin there is after X hours. Well, in every case it was 300 times 0.8, and then the power was the hour. So if there's X hours, then the exponent should be X. Okay? So in other words, if I want a formula, my formula is f of x equals 300 times 0.8 to the x power. So I could use this formula to find out how much vitamin there is left after any hour I want. If I want to know how much will be left after 10 hours, I just substitute 10 for x. How much after 15 hours? Just substitute in 15 for x. Okay, so that's the basic idea from the easier problem, coming up with this formula. Now, the harder job is coming up with the same thing when we don't know how much is being eliminated each hour. So remember, we're given the half-life of the caffeine. So we're starting with 80 milligrams, and we're told that the half-life is 5 hours. So we're told in 5 hours, half of the caffeine will be gone. That's all we know so far. So that's going to give us one of the entries on this table. All right, which one of these four numbers do we now know? Okay, I was giving you a little second to think there. We know that half will be gone after 5 hours. Well, look, 5 hours is right here. So half should be gone after 5 hours. So that means at this spot, I should have 40. Now, they're telling us to make a conjecture. That means make an educated guess. So I'm not going to do any rigorous math right now. I'm just sort of going to estimate a little bit. But I know we're going from 80 to 40 in 5 hours. So, you know, how much is going to be gone in just 1 hour? So in 5 hours, I dropped 40 milligrams. So, you know, maybe in 1 hour, I'm going to drop 10. I don't know. So maybe this is going to be 70 milligrams. And maybe this will be 55. And maybe, okay. Now this one, from 5 hours to 10 hours, this is another 5-hour jump. Okay, from 0 to 5, that was 5 hours, obviously. So it reduced by half. But from 5 to 10, that's another 5 hours. So it should reduce by half again. So, so I know this is 40, and by the time I get to 10, it should be 20. And if I went another 5 hours and I did 15, then it should be 10. All right, it's going half every 5 hours. So these two I actually know for sure. These two I'm making a conjecture. I'm guessing. And when we do come up with a formula, it'll be interesting to see how close I was, but I will surely have to come back and change these. But that's okay. They said right in the problem, you can return to your answers later, to make corrections, so I'm not going to worry about it. Let me clean this up a little bit because of, you know, OCD. Alright, now, so unlike problem number 1, where 80% remained after each hour, in this problem, 50% remains after each 5 hours. In problem number 1, what did the exponent represent? Yeah, it turned out in problem number 1, the exponent represented the number of hours, right? If it was 2 hours, the exponent was 2. 3 hours, the exponent was 3. So it was the number of hours. That was very convenient that the exponent was the number of hours, because we knew that every hour it was going to be 20% less. So it was each hour, and the exponent was the number of hours. Well, in this problem, we don't care about the number of hours. We don't know anything about that. What we know about is 5 hours at a time, 5-hour blocks. So this time, the exponent has to represent the number of 5-hour time periods. Alright, this can be tough to understand, but I'm going to try to explain one more time. On the original problem, we knew that every hour we're going to have 80% of what we had in the previous hour. Alright, so 80%. So as soon as you see, okay, it's going to be 80%, the exponent represents how many times that's going to happen. 80%, 80%, 80%, how many times? Alright, it just so happened that the 80% was happening every hour. So when we ask ourselves 80% how many times, that was going to be hours, just straight up hours. So it was simple. Now, if you think of this as cycles, alright, we're going 80%. Every time we go 80%, that's another cycle. If you think of it as cycles, this exponent will always be the number of cycles. Alright, so as we begin to set up the more difficult problem, it's going to still start off the same way. First, we write down the initial amount. So remember, we're starting off with 80 milligrams in the bloodstream. So we're going to do that first. Alright, just like before, next comes you know, the percentage that's left every cycle. So instead of 80% remaining every cycle, this time 50% is going to be remaining. And we'll put that as a decimal by doing 0.5. So all that's left is the power. Alright, this is the only thing that's going to be a little different. Now remember, we need an exponent that represents the number of cycles. So we're reducing 50%, 50%, 50%. This exponent has to be, how many times are we going 50%? How many times is 50% happening? That's the exponent. But this time, instead of a cycle being an hour, our cycles are 5 hours long. So our exponent has to be something that represents how many cycles, how many 5-hour time periods. That's what we need. And so here's what you have to do. X, here the trick is, X is still in hours. So somehow we have to convert from hours into cycles. So when we do the formula, we need to be able to put in like 1 hour, 2 hours, 3 hours. And we need the exponent to somehow turn out to be the number of cycles. So here's the thing. Sure, if we do 5 hours, that equals 1 cycle. Okay, fine. But what about 1 hour? Well, if 5 hours is 1 cycle, then 1 hour is 1/5 of a cycle. Alright? So if we did 1 hour here, we would want 1/5 here. Alright? because 1 hour is the same as 1/5 cycles. What if it was 2 hours? Well, 2 hours would be 2/5. Whoa, why did I put a 5? All right, 1 hour is 1/5 of the cycle. All right, 2 hours would be 2/5 of a cycle. Okay, remember, cycle's 5 hours long. So if I only do 1 hour, that's 1/5 of the time, 1/5 of the cycle. 2 hours would be 2/5. Okay, are you seeing the pattern yet? If I do 3 hours, how many cycles is that? 3 hours, of course, would be 3/5 of a cycle. And 4 hours would be 4/5 of a cycle. Okay, now remember when we said 5 hours was going to equal 1 cycle? Alright, will that make sense if we go to the next step? Let's see. 5 hours would be 5/5 of a cycle. But 5/5 is the same as 1. Alright, so our pattern is definitely working. Alright, however many hours, it's that many fifths of a cycle. I mean, I could keep going beyond 5. 6 hours would be 6/5 of a cycle. So here's the jump, because we need a formula for x hours. So what about x hours? Well, here it is. X hours would be x fifths of a cycle. So that's why when we make our formula, if we want a formula for x hours, then that's going to be x fifths cycles. Alright, and that's what the power has to be, the number of cycles. So x hours, x fifths of a cycle. Now I know I just blew your mind. Probably most of you did not 100% follow that. Alright, and that's because this is some next level thinking. So if you're able to follow all that, then hey, you're ahead of the game. But don't feel bad if you're listening to this and you're going, what? It's going to take a few examples. It's going to take some time for this to sink in. Alright, this is our first try, so don't feel bad if you don't fully understand. Alright, but for now, let's go ahead and move forward, even if it's a little muddy. Now, how would we use our function that we wrote in part C to answer the question in part A? Use your function to check and see if you get the same answers we did in part A. Okay, so here's our formula. Let's go ahead and look back at part A. So we were supposed to find out how much caffeine is left after 1 hour, 2 hours, 5 hours, 10 hours. And I guessed about these. These I used, common sense. But let's use the formula now. So here's our formula recopied, all ready to help us do part A. Alright, the initial amount, the percentage that we have left, the number of cycles, based on however many hours. Alright, so let's use this formula. Let's use our TI-30XS multiview. So let's hit the table button, clear this out, and type it in. So we have 80 times 0.5. Okay, let's go up to the power. Now we need a fraction up here, so let's make a little fraction mode, and so this is x fifths. Alright, so there it is. There's our formula. So we want to know, starting with 1 hour. Okay, so after 1 hour, we're going to have 69.6 milligrams. Okay, so I was actually really close. 69.6. I was guessing 70. I was actually very close. And you'll have to take my word for it, but I didn't cheat. That really was a guess, so I'm pretty amazing. So that was 69.6. Let's see how I did on the other one. Let's see if 55 is like crazy close. So let's look at the 2. Okay, not so close on this one. So on 2 hours, it should have been 60.6. So I was pretty far off. But now I'm going to fix it. $60.6. These two better be right, 40 and 20. So I'm skipping ahead and looking at 5 and 10 hours. Okay, 5 hours, there's the 40, just like we predicted, and there's the 20. Okay. So fine, we fixed it. What else do we need to do? Be careful, blah, blah, blah. Alright, so let's go on to part E. Determine the amount of caffeine in the bloodstream 3 hours after the peak. What about 8 hours? What about 20 hours? Okay. 20 hours we should be able to do in our heads. Because how many 5-hour cycles is that? Well, 20 is 5 times 4. Alright, 5 times 4 is 20. So 20 is 4 cycles. That means this 80 is going to be cut in half 4 times. Alright, cut it in half once, and you got 40. Twice, you got 20. 3 times, you got 10. 4 times, you got 5. So looking at it that way, we'd expect it to be 5 milligrams left. But let's use our formula still. I mean, it's already in our calculator, so why not? So let's look at 3, 8, and 20. Alright, so first of all, here's 8 is 26.4. I'm going to round up. Alright, let's look at 3 and 20. Alright, 3, after 3 hours is 52.8. Got to round up. And let's look at 20 and make sure that it's 5. And it is. Alright, well, suppose the half-life of caffeine was 3 hours instead of 5. Okay, well, the rest of it is staying the same. We're supposed to write another formula. So we're still going to go f of x. The original amount is still 80. Alright, we're still talking about half-life, so we're still talking about 50%. Alright, so that means 0.5 is 50%. So the only thing that will be changing is the exponent. When the half-life was 5 hours, then each hour was however many fifths of a cycle. When the half-life is 3 hours, then 1 hour would be 1/3. 2 hours would be 2/3. X hours would be X thirds. Okay? So basically, whatever this number is in the denominator, that's going to be your half-life. Okay, so that would be our new function. So determine the amount of caffeine after 1, 2, 5, and 10 hours. And, we'll just use our new formula to figure that out. Okay, back to the table. I think we can just go in and just edit that one number, change it to a 3. Okay, let's start at 1. Alright, so with the new formula, after 1 hour, we will have 63.5 milligrams. Got to round up. $63.5. What about 2 hours? That's 50.4. Got to round up. What about 5 hours? 25.2. What about 10 hours? 7.9 milligrams. Now, which half-life results in the caffeine being eliminated faster? Explain why this makes sense. Well, in the first situation, half of the caffeine is gone in 5 hours. In the new situation, half of the caffeine is gone in 3 hours. So, obviously, half of the caffeine being gone in 3 hours is faster than 5 hours. So, yeah, half the caffeine gone in 3 hours is faster than half gone in 5 hours. Same amount gone in a shorter amount of time. It just makes sense. But let's look at the numbers, because we have the same numbers here. For example, under this new system where we have a 3-hour half-life, after 10 hours there are 7.9 milligrams left. Looking back at the 5-hour half-life, alright, after 10 hours there were 20 milligrams left. Okay, so same amount of time, but this one has more left, so that means this one is eliminating faster, just like you would think. Graph both equations from D and F on Desmos.com, or use the Desmos app on your phone. So let's graph the two functions. You know, the one with the half-life of 3 hours and the one with the half-life of 5 hours. Let's graph them both on Desmos. Okay, so first I will graph the I'll graph the 5-hour one. So say if we have y equals, and so we had 80 times 0.5, and the power, I'll use this button just to get me up to the power. But I need a fraction now. So I need x divided by 5. You're not seeing a graph right now because this is too zoomed in. I'm only looking at 5 units, but we have 80 is going to be the starting amount. So we need to zoom in such a way that we can see what we're doing. Okay, so this is better. So here's the first graph with half-life of 5 hours. Now let's do the second one. So y equals 80 times 50%. Let's get into the exponent, and this time we'll do x divided by 3. Okay, let me see if I can zoom in on this a little bit more, but just remember the red one is the one with the 5-hour half-life, and the blue one is the 3-hour. Alright, there's a pretty good view of it. So you can see the one with the 3-hour half-life, you can see it dropping faster. So let's see, what do they want to know about it? How are the graphs similar? How are they different? Okay, how are the graphs similar? Well, they're similar. They are both exponential functions. Hopefully you learned about that last year. Both of these are exponential decay functions. Alright, other than the fact that they're both exponential decay, do you notice anything else that's the same about both graphs? I mean, we could say a whole bunch of things like both of them stay above the x-axis the entire time. They both have the same y-intercept. They both start out at 80. They both have a y-intercept of 80. All right, which makes sense since they both start with 80 milligrams. So there's a whole bunch of things you can say. Your answer here doesn't have to match mine. Just make your own observations. Now, how are the graphs different? Well, like we said before, the 3-hour half-life function is dropping faster. What are the intercepts? Well, we already saw that they both have a y-intercept of 0, 80. They don't have any x-intercepts at all. These graphs seem to be getting closer and closer to the x-axis, but if you zoomed in far enough, you would see that they're not actually touching. So what are the intercepts? They both have a y-intercept of 0, 80. When are they increasing? Nowhere. These graphs are both decreasing the whole way. Oh, look, that's something else they had in common that we could have said. They're both decreasing over the entire function. All right, downhill, downhill, downhill in both cases. So where are they increasing? Nowhere. Where are they decreasing? Everywhere. I mean, I could have just said everywhere. Are there asymptotes? If so, what are they? What's an asymptote? Well, isn't the asymptote that line where if you're getting closer and closer to it, but actually never touching? So the x-axis is the asymptote for both of these graphs. Do the graphs intersect? Yeah. Since they both have the same y-intercept, that's where they intersect. What about down here? It seems like they touch down here. Well, no, they don't. If you zoomed in, which I'm not sure how well I can do that. I'm going to try. Okay, if you look at a spot where they seem to touch, okay, like take this spot right here at 50. Somewhere around 50 kind of looks like they touch, right? But let's zoom in closer and take a closer look at 50. Once you zoom in closer, you see, oh, nope, there's a little bit of a gap there. They're not touching at 50. Do they touch over here then? Okay. Aha! Looks like they touch at 60. Do they touch at 60? Do they touch at 60? Oh, look at that. When we zoom in, we see that they don't really touch at 60. Do you get the point? I could do this all day. These lines are going to look like they are touching sometimes because they get so close together that you can't tell. But if you zoom in, you'll actually see that nope, they don't touch. So no, the lines never touch. There is no intercept down here. They never touch. And the graphs only intersect at 0, 80. That's it. All right, and that's going to be the end of this lesson. This video is much longer than I'd like them to be, but it was just a complicated topic. So if you were able to follow everything I did, then congratulations. You are on the next level. If I lost you somewhere along the line, don't feel bad. We'll get there by the end of the year.